In this video, I'm going to try to put the math together for how some of these things came about. In particular, Planck's constant, which started the whole thing of quantum mechanics back in 1900. Now, first I'm going to go over Wien's law, then I'm going to look at Boltzmann's law and Boltzmann's equation, and then finally come up with how Max Planck came up with his final constant. And I'm going to do these in uh, one video after another that shows these different items. So hang on, let's see if it works out. Okay, we're going to start with Wien's law. And you'll notice here that got these different uh, plots here, and they're labeled 5500K, 5000K, 4500K, 4000K, 3500K. Each one of these is a temperature, a Kelvin temperature, which is absolute temperature. Now, what the Wien's law shows is that there's a certain peak for each one of these dependent on temperature. Now, the peak is for a frequency or a wavelength. Wavelength goes low, that means frequency is high. And if you look at these peaks, the peak of 3500K is different than 4000K is a different. In other words, the peaks move to the left. So let's go ahead and write up here Wien's law. And Wien's law says that the wavelength peak is equal to a constant, Wien's constant, over temperature. Now, let's examine this a little bit and see what happens. As temperature increases, the peak will decrease, and the wavelength means that the frequency is higher for those things. That's all that Wien's law did. Now, the important. Okay, as promised, here's the formula that we had from the last one. Here's the wavelength peak, and this is Wien's constant, or Wien's constant. He's German, so let's pronounce it correctly. And here's the idea that Planck had to match up with this peak value. Here's his constant times frequency over the natural logarithm base Planck's constant times frequency over kT. Now here's a new constant, k. Where does this k come from? Well, there's several different ways that I can come up with where the k constant came from, or Boltzmann's constant, but let's look at this one. Ideal gas law. Pressure times volume equals N, where N is the number of moles of gas. Now, that might not be something you know about, but let's just go ahead and run with it. That's the number of moles of gas times the gas constant times the temperature. This was something that was arrived at fairly early. Now, if we take that R and define it as Avogadro's number, which is Avogadro's number is the number of atoms in a mole, and multiply that times K, that gives us the constant that fits in here. So let me just summarize this in kind of a really rough way so that the ideas that came out of this formula here, which seems kind of wild, is that it came from the study of energies in a gas. And so, using those same kind of statistical methods, we come up with this relationship here, which holds true for the spectral intensity of those different frequencies. Now, there's another equation that goes along with this called the Rayleigh-Jeans, which I covered in some of my lead up into photons, but this is the one I wanted to get to. Now, how is this going to peak out? Seems with increasing frequency, the energy is going to go up, going to go up, going to go up. Well, what about this? Well, if we look at this, if we have increasing temperature, then there's going to be some relationship between this constant times the frequency that's going to come up with a value that will eventually reach a peak, and then it'll start dropping off. The best way I can describe it is the frequency is going to be a linear relationship, whereas this is going to be an exponential relationship. And as that exponential relationship starts growing really big, then what that's going to do is drag the energy down, and it'll give us that peak performance that we saw in the last part of this video. This might not make too much sense now, but I'm still trying to find a way to express this information in a quick way.